Hello everyone, welcome back to my Continuum mechanics lectures. Today we will be looking at some problems related to kinematics. So let's look at some problems. So we will look at problems number 2, 3 and 5. So the first problem is that let J is determinant F, let J be determinant F, show that J dot by J is trace of L. So let's see. So this is problem number 2. So J is determinant F, which implies that J dot is determinant F dot of determinant F, which implies that J dot is del by del F using the chain rule of determinant F dot. This quantity, as we have already seen before, is nothing but the cofactor of F. Therefore, J dot is F star dotted with F dot. Now as F is invertible, F inverse, the inverse of F exists, and F inverse is defined as in terms of cofactor 1 by determinant F into transpose of the cofactor of F, which is F star transpose divided by J. So as we have seen earlier, that J dot is F star dot F dot. This is trace of F star transpose F dot. So according to this expression, this is nothing but trace of J times F inverse F dot. We can take J outside because it is a scalar. Trace of F inverse LF, as we have seen already in the lecture that F dot is LF, where L is the gradient of spatial gradient of velocity in spatial description. Therefore, using the properties of trace, we can write this as trace of L F F inverse. We are just alternating between these two matrices, these two tensors. So therefore, taking F and F inverse together, we have J trace of L. This proves that J dot by J is nothing but trace of L. So that solves our first problem. Now we come to the second problem, which is problem number 3. So let me read out the question. So to analyze complicated deformations, it is sometimes helpful to view the deformation as a succession of simpler deformations. That is, a deformation from capital X to small x could be viewed as a deformation from capital X to x tilde followed by a deformation from x tilde to small x. If f tilde is a gradient of the first deformation and f hat is the gradient of the second deformation with x tilde as the reference position, show that gradient of f of the total deformation is f is equal to multiplication of the two tensors f hat and f tilde. So let's see this first part. So basically what we have is that from a reference configuration, we using the deformation gradient f tilde, we go to x tilde, which is an intermediate configuration, and from that we go to f hat, which is the current configuration. So according to our definition of uh, deformation gradient, we have that dx tilde is f tilde d of capital X. Similarly, d small x is f hat of dx tilde. So using this definition, we write dx is f hat dx tilde, and then using this definition here, this is 1, this is 2, we have f hat f tilde d capital X. Therefore, this becomes f tilde f tilde d capital X. If we write this as a single deformation gradient from capital X to small x, then as d small x and d capital X are arbitrary, f becomes f hat f tilde. Now let us look at the next parts of the question. So use this result to find f, c and b for the problem of combined extension and torsion of a solid circular cylindrical bar made of an incompressible material, that is a material capable of undergoing isochoric deformations only. This means that all the f's, say f hat, f bar, f tilde, have the determinant as 1. So initially we start as take capital X to be r er as a function of big theta plus x3 k cap. So suppose the bar is first stretched uniformly to lambda times its original length with accompanying lateral contraction. So that's x tilde is small r er capital theta plus x3 k cap, with x3 as lambda capital X3 and r as f of capital R, some function of r. Suppose the bar is then twisted into, so there are two deformations. First is a stretching of the bar along its axis. The second is then twisted into the position x small x r er small theta plus x3 k cap, where theta small theta is big theta plus psi times x3, and er theta is given as cos psi x3 er capital theta plus sin psi x3 e theta capital theta. Here psi is the constant angle of twist per unit length about the k axis. So let's write down the let's find out first the f, f hat and f bar. So capital X is given as r er capital theta plus capital X3 k cap. X tilde is given as r er theta plus small x3 k cap, where small x3 is lambda capital X3 and r is some function of capital R, and small x is given as r er small theta plus x3 k cap, where theta small theta is capital theta plus psi x3, er theta is cos psi x3 er capital theta plus sine psi x3 e theta capital theta. Psi is constant. So let's calculate f bar first, which is the second deformation. That is from x tilde to x. So x is r cos psi x3 er capital theta plus sine psi x3 e theta function of capital theta plus x3 k cap, and x tilde is RER capital theta plus x3 k cap. Therefore, writing d small x is dr cos psi x3 er capital theta plus sine psi x3 e theta capital theta plus r cos psi x3 e theta capital theta d theta. The same method we have done in solving problems in the previous problem solving sessions. So you can have a look at the previous lectures. Sin psi x3 er capital theta. This should be okay. This is d capital theta plus minus psi sin psi x3 er theta plus psi cos psi x3 e theta capital theta times dx3 plus dx3 k cap. This is because del by del capital theta of er capital theta is e theta capital theta, and del by del capital theta of e theta capital theta is minus er capital theta. So in a fixed basis, e1 e2 e3 er theta is nothing but cos theta e1 plus sin theta e2. Similarly, dx tilde can be written as dr er capital theta plus r d capital theta e theta plus dx3 k cap. Therefore, dr can be written as dx tilde dotted with er capital theta d capital theta can be written as dx tilde dotted with e theta capital theta by r, and dx3 can be written as dx tilde dotted with k cap. So using these expressions in the above expression, in the last expression of dx, which is this one, we have dx as dx tilde dot er theta times cos psi x3 er theta plus sin psi x3 e theta theta plus dx tilde dot e theta theta by r times r cos psi x3 e theta function of capital theta minus sin psi x3 er capital theta, so r cancels, plus dx tilde dotted with k cap in place of dx3 times minus r psi sin psi x3 er capital theta plus r psi cos psi x3 e theta capital theta plus k cap. Therefore, writing this in terms of the dyadic product, we obtain that dx is nothing but cos psi x3 er capital theta plus sin psi x3 e theta capital theta, dyadic er function of capital theta plus minus sin psi x3 er capital theta plus cos psi x3 e theta capital theta, dyadic e theta of capital theta plus r psi minus sin psi x3 er capital theta plus cos psi x3 e theta capital theta plus k cap dyadic k cap times dx tilde. Therefore, f hat in terms of the er theta e theta theta k cap basis can be written in a matrix form as cos psi x3 minus sin psi x3 minus r psi sin psi x3 sin psi x3 cos psi x3 r psi cos psi x3 0 0 1. This is f hat. Similarly, I won't go into the whole calculation again. F tilde, that is from x to x tilde, can be written as dx tilde is equal to f dash r er theta dyadic er theta plus lambda k cap dyadic k cap plus fr by r e theta dyadic e theta times d capital X. Therefore, f tilde again in sorry er, we write this again, er theta e theta theta k cap basis can be written as in matrix form f dash r 0 0 0 fr by r 0 and 0 0 lambda. So now, according to our first part of the question, find f, c and b. Now both f tilde and f hat are written in the same basis er e theta k, so they can directly be multiplied. Uh, we can directly, so there's no need to change the basis for either of them. We can directly multiply the above matrices to get f, and hence c, which is f transpose f, and b, which is ff transpose. Let's look at the other parts of the question. So find fr in terms of lambda. The first question A is find fr in terms of lambda. So we know that the material is incompressible. Let's do it partwise. As the material is incompressible, the volume remains constant upon any deformation. Therefore, determinant of f tilde is equal to 1, which implies that f dash of r times fr by r times lambda is equal to 1, which means that f of r d f of r by dr is r by lambda, which implies that f df is r by lambda dr. So r goes from 0 to r, or we can do it as an indefinite integral. Therefore, which implies that f square by 2 is r square by 2 lambda plus a constant c. Now to maintain continuity at the center, as there is no cavitation, there is no cavity forming, there is no cavitation. For r is equal to 0 should imply small r is equal to 0. That is, f of 0 should be 0. This implies that c is 0, and therefore the form of function f is r by root lambda. And only the positive sign is taken because f of r should be greater than equal to 0, as r is greater than equal to 0. R is a positive quantity. So r is equal to f of r by root lambda. Let's look at the next part, which is show that f hat may be written as the product of a rotation and a simple shear. So this is our f hat. This is our f hat. And we know that all deformations are incompressible. That is, determinant of f bar is equal to 1, which is greater than 0, which implies that we can use the polar decomposition theorem on f hat. So f hat is r hat u hat, let's say. So we already have a rotation here. Now we need to prove that u is a simple shear. Now u hat is obtained as u hat square is f transpose f, which is c. Let's say it is c hat. So you can easily calculate, you can easily multiply f transpose f. So this is f hat transpose f hat in terms of the er e theta k cap basis, that this comes out to be 1 0 0 0 1 r psi 0 r psi 1 plus r psi square. So therefore u hat can be calculated in the same basis, er e theta k cap, as 1 0 0 0 1 r psi 0 0 1. This is the form of a simple shear. This we have already seen in the lectures as an example. Hence, this proves that f hat can be written as a rotation, as product of a rotation and a simple shear. Let's look at the next part. Verify that the deformation from x to x, small x, is isochoric. Now, given the form of the function f of r, which was r by root lambda, we have f tilde in the er e theta k cap basis as 1 by root lambda, 1 by root lambda and lambda. Determinant of f tilde is 1 by root lambda square times lambda, which is 1. Therefore, this is isochoric. Also, f hat, or determinant of f hat is determinant of cos psi x3 minus sin psi x3 minus r psi x3 sin psi x3 cos psi x3 r psi cos psi x3 0 0 1. It can be easily seen that this is nothing but cos square psi x3 plus sin square psi x3, which is 1. Therefore, determinant f, which is equal to determinant of f hat f tilde, which is equal to the product of the two determinants times determinant f tilde, is 1 1, which is 1. Therefore, f, the deformation gradient, from capital X to small x is isochoric. Let's now look at the last question. So consider an isochoric deformation of the form x is equal to chi of capital X, which is 1 by r fr x, where r is mod x. Show that a spherical surface r is equal to constant in the reference configuration is mapped to a spherical surface in the current configuration. So let's see that first. This is question number 5. So x is given as f of r by r capital X, which is f of r x by mod x, which is f of r times e, where e is the set of all unit vectors. So for a point on the spherical surface in reference configuration, any point can be given as RE, which is KE, where K is a constant. So for a spherical surface, R is constant K, which means R is equal to K for all points in the reference configuration. So now, given the motion, small x is chi of capital X is f of r e, which is f of k e, which is another constant k1 times c. As k is constant, so f of k stays constant for all the points in the current configuration as well. So this means that x is another spherical surface with radius r is equal to k1, which is fk. Therefore, we have proved that the given deformation maps a spherical surface r is equal to constant in the reference configuration to a spherical surface in the current configuration. Let's look at the second part of the question. So suppose the body contains a spherical cavity of radius capital R is equal to capital A in the reference configuration. Let A be the deformed radius of this cavity. Assuming that A is known, find f of R, capital deformation gradient f, u, v, r, and the principal stretches. So we know that mod of x is equal to small a when mod of capital X is equal to a. There is a spherical surface of the cavity of radius a, radius capital A, is mapped via deformation chi to a spherical surface again of the cavity of radius small a. Therefore, mod of x when mod of capital X is equal to a is small a, that is f of a by a mod of x is equal to a, which implies that f of a by a mod of x when mod of x is a, which implies that f of a is small a. Now let us calculate the deformation gradient f. So using spherical coordinates, so we have it can be easily shown using our method that x is r I theta of theta and phi, where I, theta and phi are given as cos phi er theta plus sin phi e3. Er theta is cos theta e1 plus sin theta e2 in a fixed basis. Del by del theta of er theta is e theta. So it can be easily seen that dx can be written in terms of capital D capital X as f dash r using our usual manipulation I dyadic I plus f of r by r e theta dyadic e theta plus e phi dyadic e phi. dx. Therefore, deformation gradient is given as f dash r I diatic I plus fr by r e theta diatic e theta plus e phi diatic e phi. So writing f in terms of the basis as a matrix form, I, e theta and e phi comes out to be f dash r fr by r and fr by r on the diagonal terms, rest are 0. So as the deformation is isochoric, determinant f is 1, which implies that f dash r times f of r by r whole square is 1, which implies that f square df is equal to r square dr. Taking an integral on both sides, we have f cube by 3 is r cube by 3 plus some constant c. Now we have already have a boundary condition that f of a is equal to small a. Therefore, a cube by 3 is capital A cube by 3 plus c, which implies that c is a cube minus capital A cube by 3. Therefore, fr comes out to be of the form r cube plus a cube minus capital A cube power 1 by 3. So this is the form of fr obtained. Now with this information, and that determinant f is greater than 0, which is it's 1, so it's greater than 0, we can calculate f easily using this expression in terms of in a matrix form. So f is obtained, and by polar decomposition, as determinant f is greater than 0, we can easily obtain u, v and r, given the formula that f is equal to ru is equal to vr. So that brings us to the end of this problem solving session. Next we will discuss balance laws. Thank you.